You have seen this image 1,000 times. A fighter jet sits on the deck of an aircraft carrier. Steam curls from the track ahead. 2 seconds of silence. Then the aircraft is hurled forward from standstill to 165 miles per hour and flung off the bow into open air. It is the single most reproduced image of American military power. Every film about naval aviation features it. Every news broadcast covering a carrier deployment opens with it. The mechanism that makes it happen, the steam catapult, sits on 10 of America's 11 aircraft carriers in active service today. It has launched every naval combat aircraft the United States has flown since 1954, every strike against North Vietnam, every sortie over Iraq, every patrol over the Taiwan Strait. The man who invented it was a Scottish engineer working from a factory in Edinburgh. His name was Colin Campbell Mitchell. He has no biography, no documentary, no Wikipedia article of consequence. The device that defines American naval supremacy was designed in Scotland, and virtually no one in America or Britain could tell you by whom. To understand why Mitchell's catapult mattered, you have to understand the crisis it solved. And to understand that crisis, you have to forget everything you know about modern carrier aviation and go back to a world where launching an aircraft from a ship was a problem of ropes, pulleys, and compressed air. During the Second World War, carrier aircraft were propeller-driven. A Seafire weighed roughly 3.5 tons. A Corsair, 4.5. These were light machines, and they had one critical advantage that post-war jets would lose entirely. The propeller itself generated airflow over the wings at low speed. Even sitting on the deck with the brakes locked, a propeller aircraft was already producing a measure of lift before it moved an inch. Catapults helped. They shortened the takeoff run and allowed launches in calm wind. But a competent pilot in a Seafire could in a pinch get airborne from a carrier deck without one. The jet engine changed the arithmetic overnight. A de Havilland Sea Vampire weighed 5 tons. A Supermarine Attacker just over 5.5. The Hawker Seahawk pushed past 6. These aircraft had higher stalling speeds, which meant they needed to be moving faster before their wings generated enough lift to fly. And they had no propeller wash, no free airflow at low speed. A jet fighter sitting on a carrier deck with its engine at full power was producing thrust, but generating almost no lift until the aircraft itself was moving. The catapult was no longer a convenience. It was the difference between flying and swimming. The Royal Navy's standard catapult at the end of the war was the BH-5, a hydropneumatic system that had served adequately for a decade. The principle was straightforward enough. Compressed air drove a piston inside a cylinder, and the piston was connected by wire ropes running over a series of pulleys to a shuttle that ran along a track in the flight deck. The shuttle was attached to the aircraft. The valve was opened, compressed air shoved the piston, the ropes hauled the shuttle, and the shuttle dragged the aircraft forward until it reached flying speed. The problem was weight, not the aircraft's weight, but the catapult's own. Commander W.R. Stewart, writing in the Journal of Naval Engineering in 1953, laid out the mathematics with painful clarity. In the BH-5, the wire ropes, pulleys, and other moving parts weighed the equivalent of 17,000 pounds. Every launch, the catapult had to accelerate that 17,000 pounds to full speed alongside the aircraft, and then decelerate it all again at the end of the stroke. Stewart calculated that any attempt to scale the system up for heavier jets would approach a point where the catapult spent all its energy accelerating itself. The aircraft would be an afterthought. There were other problems. Wire ropes wore out, pulleys jammed. The hydraulic fluid used in some American systems was flammable. And the US Navy had recorded fatalities when ruptured lines sprayed burning fluid across the deck. Maintenance was relentless. Every component in the rope and pulley train was a point of failure, and carriers at sea had limited capacity to manufacture replacement parts. The system that had launched Swordfish torpedo bombers against Bismarck was reaching a wall that no amount of incremental improvement could breach. The Americans knew this. By the late 1940s, the US Navy's Bureau of Aeronautics was working on its own next-generation Catapult, a slotted tube design powered not by steam, but by cordite charges, essentially a controlled explosion, driving a piston down a cylinder. The concept had a certain brute logic. Gunpowder contained enormous energy in a small volume, and the US Navy had decades of experience handling explosives aboard warships. Development contracts were awarded and prototypes built. The results were disappointing. Explosive catapults were violent, difficult to calibrate precisely, and wore out their components at alarming rates. Buer persisted, partly from institutional momentum, and partly because they had explicitly considered and rejected steam as a power source. The reasoning was technical. American warships used high-pressure, high-temperature boiler systems, and the engineers at Buer believed that diverting steam from these systems to a catapult would be impractical. And meanwhile, the clock was running. The Douglas A-3D Sky Warrior, a nuclear bomber designed to strike the Soviet Union from carrier decks, was entering production. It weighed over 30 tons. No hydraulic catapult could launch it. The explosive catapult was failing. The US Navy was building the most expensive warships in human history around an aircraft they could not get into the air. Colin Campbell Mitchell was born in Edinburgh in 1904, the son of John Campbell, Mitchell RSA, a landscape painter of sufficient distinction to have his work hung at the Royal Scottish Academy. His elder brother, Lieutenant John Patrick Cameron Mitchell of the Royal Flying Corps, was killed during the Second Battle of Arras in April 1917. He was 19. Colin was 13. Whatever that loss did to the boy, it did not push him away from military service. It pulled him toward the machinery of war. He attended Edinburgh Academy, then read engineering at the University of Edinburgh, graduating with a BSc in 1925. That same year, he joined MacTaggart, Scott and Company in Loanhead, a small town 8 miles south of Edinburgh. MacTaggart Scott built hydraulic machinery, deck equipment, steering gear, submarine systems, and it was here that Mitchell first encountered the engineering of aircraft catapults. By 1931, at 27, he was technical director. That year, his hydraulic arresting gear was tested aboard HMS Courageous, one of the Royal Navy's 3 fleet carriers. The Admiralty took notice. Here was a young Scottish engineer who understood the specific mechanical violence of stopping a moving aircraft on a pitching deck, a problem that combined hydraulics, metallurgy, and a tolerance for forces that would tear most machines apart. In 1933, Mitchell filed a US patent for catapult retarding gear. In 1936, he filed something more significant, a patent for a slotted cylinder catapult design. The concept was deceptively simple. Instead of ropes and pulleys connecting a piston to a shuttle, the piston itself would drive the shuttle directly, its arm reaching upward through a slot running the length of the cylinder. No ropes, no pulleys, no 17,000 pounds of dead weight being hauled back and forth with every launch. The Admiralty reviewed the concept and acknowledged it as sound. Then they declined to develop it. The reasoning was not unreasonable. Existing hydraulic catapults handled the biplanes and light monoplanes of the 1930s perfectly well. Why invest in a radical new system for a problem that did not yet exist? The war intervened. Mitchell joined the Royal Naval Volunteer Reserve in 1941 as a lieutenant commander in the engineering branch, attached to the Engineering Chiefs Department at the Admiralty. Promoted to commander in 1943, he became responsible for all flight deck machinery on Royal Navy carriers. Every arresting gear system that caught a landing aircraft on a British deck during the war was his design. He served in Washington liaising with the US Navy, with the British Pacific Fleet in the final months of the Pacific Campaign, and in France and Germany after liberation. It was this last assignment that changed everything. In 1945, Mitchell was sent to inspect V-1, flying bomb launch sites in northern France and Germany, as part of the British Intelligence Operational Survey Team. The V-1 had terrorized London for months, a crude cruise missile launched from fixed ramps along the Channel coast. What Mitchell found at those ramps was a slotted cylinder catapult. The Germans had arrived at the same principle he had patented in 1936, though their version was powered by hydrogen peroxide rather than steam, was enormously heavy and was designed to be used once or twice before being replaced. It was a disposable sledgehammer, but the core idea, piston, slot, direct drive, was identical. Mitchell collected components through BIOS and brought them back to Britain. He now had something more valuable than a patent on paper. He had physical proof that the slotted cylinder principle worked at the scale and energy levels needed for heavy payloads. The German catapults had launched V-1s weighing nearly 2.5 tons to speeds above 200 miles per hour. An aircraft catapult would need to do more. Heavier loads, higher speeds, thousands of cycles instead of a handful. But the fundamental physics had been demonstrated by the enemy. Upon demobilization in 1946, Mitchell joined Brown Brothers and Company on Broughton Road, Edinburgh, as technical director. The Admiralty awarded Brown Brothers the development contract for a steam-powered, slotted cylinder catapult, specifically because Mitchell had joined the firm. The company was a respected Edinburgh engineering house. Hydraulic presses, deck machinery, industrial equipment, but it was not an obvious choice for what amounted to building a weapon-grade launch system. Mitchell was the reason. The contract followed the man, not the company. He was, by every account, a particular kind of engineer, the kind this channel keeps finding in the margins of history. An accomplished watercolorist whose paintings were exhibited alongside his father's at the Royal Scottish Academy. A colleague described him as possessing all the rare qualities of the truly creative engineer: vision, a lover of the arts, a sense of what was really practicable, and meticulous attention to detail. The phrase, "a sense of what was really practicable," is the one that matters. Mitchell was not a theorist sketching concepts for other people to build. He was a man who had designed arresting gear that caught aircraft on pitching decks in the North Atlantic, who had crawled through wrecked V-1 launch ramps in liberated France, and who understood that a catapult which worked beautifully in a laboratory was worthless if it could not survive saltwater, rolling seas, and a maintenance crew working under combat conditions. The engineering problem was this: take a jet aircraft weighing between 6 and 15 tons, accelerate it from 0 to at least 120 knots within 150 feet of deck space, do it smoothly enough that the pilot remains conscious and the airframe remains intact, do it reliably enough that it works 20 times a day in any sea state, and do it using equipment that can be maintained by sailors rather than laboratory technicians. Mitchell's solution used 2 parallel steel cylinders, each roughly 18 inches in diameter, lying side by side in a trough recessed beneath the flight deck. Inside each cylinder ran a piston. From the top of each piston, an arm extended upward through a narrow slot running the full length of the cylinder. The 2 arms connected to a single shuttle, a heavy steel block that ran in a track flush with the deck surface. The aircraft was attached to the shuttle by a wire bridle hooked under the wings. When the launching valve opened, steam flooded into the cylinders from large receiver drums positioned below the flight deck, driving both pistons forward simultaneously, which drove the shuttle, which dragged the aircraft. The slot was the design's most vulnerable point and its most elegant solution. A continuous opening in a pressurized cylinder is, in engineering terms, an invitation to catastrophic failure. Mitchell sealed it with a flexible steel strip, a narrow band that lay flat over the slot, held in place by the steam pressure itself. As the piston passed beneath, small guide wheels on the piston arm lifted the strip just enough to let the arm through, and the strip fell back into place behind it. The seal was never perfect. Some steam escaped, and crew on the flight deck learned to stay clear of the track during launches, but it was effective enough to maintain working pressure throughout the stroke. The steam came from the ship's own boilers. This was a crucial design choice. Mitchell did not require a separate power plant, a chemical charge, or an explosive cartridge. Every steam-powered warship already carried the energy source. Receiver drums, large pressurized tanks, were charged between launches, storing enough steam for a single shot. The charging cycle determined the interval between launches, roughly 2 to 3 minutes on early systems, reduced to under a minute on later marks. The advantages over hydraulic catapults were not incremental. They were transformative. The moving mass of the slotted cylinder system was a fraction of the rope and pulley arrangement. Where the BH-5's moving parts weighed 17,000 pounds, Mitchell's pistons and shuttle weighed far less, meaning nearly all the steam's energy went into accelerating the aircraft rather than the machinery. The acceleration profile was different too, and this was something pilots noticed immediately. A hydraulic catapult delivered its peak force at roughly 1/3 of the shuttle's travel, producing a savage initial jolt that could blur vision and compress spinal discs. Mitchell's steam catapult reached peak acceleration at approximately 2/3 of the stroke, producing a progressive buildup that pilots compared to riding on a feather mattress. The phrase was not metaphorical. It appeared in official Royal Navy pilot reports. Energy output was scalable by adjusting steam pressure. A light aircraft needed less pressure, a heavy bomber needed more. The same catapult could launch a 6-ton fighter in the morning and a 15-ton strike aircraft in the afternoon without mechanical modification. The operator simply turned a valve. This flexibility alone would have justified the design, but it was the stopping problem that demonstrated Mitchell's engineering at its most precise. Consider the forces involved. The shuttle, pistons, and connecting arms, roughly a ton of steel, reached speeds above 120 knots by the end of the power stroke. The aircraft separated from the shuttle at the bow. The shuttle did not. 1 ton of metal at 120 knots had to stop within 5 feet. If it overran, it would punch through the end of the cylinder and wreck the flight deck. If it stopped too gradually, the cylinder would need to be longer, and carriers did not have unlimited deck space. Mitchell solved it with water-filled retardation cylinders and tapered spear-shaped rams at the forward end of each power cylinder. As the pistons reached the end of their stroke, the rams entered the water cylinders, forcing water through progressively narrower orifices. The deceleration was approximately 800 times the force of gravity. Below decks, the sensation of a catapult launch was distinctive. A deep, percussive thud that one engineering officer compared to a heavy naval gun being fired directly overhead. The entire system, cylinders, pistons, sealing strips, receiver drums, launching valves, retardation gear, deck track, shuttle, was designed to be manufactured by a commercial engineering firm in Edinburgh, installed in a warship operated by naval ratings, and maintained at sea with standard tools. This was not a laboratory demonstration. It was an industrial product, and it worked. Shore-based testing began in 1946, using a prototype partially constructed from the V1 components Mitchell had retrieved from France. The Armament Research Establishment, part of the Ministry of Supply, provided facilities and cooperation. By 1950, the prototype had launched enough dead loads to convince the Admiralty that the next step required a ship. They chose HMS Perseus. She was a Colossus-class light fleet carrier, originally laid down during the war, but completed as an aircraft maintenance ship rather than a frontline combat vessel. She was available, she was expendable in the sense that no operational squadron depended on her, and her flight deck was long enough for a meaningful trial. Captain H.A. Trial, CBE, took command on the 22nd of June 1950, and the prototype Catapult, designated BXS-1, was installed in a new structure on the forward flight deck during a refit at Rosyth Dockyard in early 1951. The trial program was methodical in a way that tells you a great deal about the people who designed it. They did not begin by launching aircraft. They began by launching weighted trolleys, deadloads of increasing mass, fired off the bow and into the sea, each one instrumented to measure acceleration, peak force, and shuttle velocity. Only after the deadload program established that the catapult performed within predicted parameters did they move to the next phase, which was considerably more dramatic. 6 surplus Supermarine Seafire F-47 fighters were prepared for unmanned launches. Their wings were removed at the fold joint to prevent them from generating lift, but their engines were run at operating power with 20-gallon fuel loads, simulating the weight and thrust conditions of a real launch. One by one, they were placed on the shuttle, the launching valve was opened, and the Seafires were hurled off the bow of Perseus into the Firth of Forth off May Island. One of the 6 famously refused to cooperate with the program's intentions. Its engine running at full power, combined with residual aerodynamic surfaces to produce enough lift that the Seafire climbed after launch, turned back toward the ship, and had to crash into the sea before it reached the flight deck. The last 2 in the series were deliberately sabotaged before launch. One had its tailplane damaged with an axe, the other had a single flap lowered, to test how the catapult performed when the aircraft's aerodynamics were compromised. Both launched successfully. Manned launches followed. The aircraft types read like a cross-section of the Royal Navy's post-war inventory: Fairey Firefly Mark 5s and 6s, Grumman Avengers, the American torpedo bomber still in British service, Supermarine Attackers, the Navy's first operational jet fighter, de Havilland Sea Hornets, Hawker, Sea Furies, short sturgeons, a heavy twin-engine reconnaissance aircraft that was among the most demanding types in the fleet. Over the full trial period, Perseus completed 1,560 launches. 355 were light shuttle tests, 1,039 were deadloads, 166 were manned aircraft. Not one resulted in an accident, not one damaged an aircraft or injured a pilot. For an entirely new launch technology, on a ship that had never been designed to carry it, the record was as close to flawless as experimental engineering permits. The numbers were convincing. The audience that mattered, however, was not in Britain. The US Navy had been watching the British program with a mixture of professional interest and institutional skepticism. Buea's own powder catapult was struggling. The deadline for the A-3D Sky Warrior, a 30-ton nuclear bomber that would be useless without a catapult powerful enough to launch it, was approaching with no American solution in sight. But steam remained, in the minds of Buea's catapult specialists, a technology that would not work with American high-pressure boiler systems. Rear Admiral Apollo Suchek, the US Naval Attaché for Air in London, saw the Perseus trials and understood what he was looking at. Susek was not a bureaucrat. He was an aviator. He had held the world altitude record in 1930. And he grasped immediately that the British had solved the problem his own navy could not. He personally arranged for Perseus to cross the Atlantic and ensured that the Chief of Naval Operations understood that a working alternative to the failing powder catapult existed and was available for demonstration. Perseus arrived at Philadelphia Naval Shipyard on the 14th of January, 1952. The test program the Americans designed was not gentle. They wanted to know whether British equipment could handle American steam at American pressures. The destroyer USS Eugene A. Green was moored alongside and connected to the Catapult's receiver drums, supplying steam at 550 pounds per square inch, significantly higher than the pressures used during British trials. The Catapult handled it without modification. It was, as the official report noted, readily adaptable. Then they brought in the pilots. Captain Eric Brown, Winkle Brown, was at this point on exchange duty at the U.S. Naval Air Test Center at Patuxent River, Maryland. Brown held the world record for the most carrier deck landings by any pilot in history, a record that still stands. He flew a Grumman F-9F Panther from the Perseus catapult at 126 knots and 4.3 times the force of gravity. The ship was tied up dockside. There was zero wind over the deck, no forward motion, no headwind, nothing but raw catapult energy and a jet engine. Brown, who had flown more aircraft types than any pilot alive, described the launch as smooth. The at-sea demonstrations followed in February off the coast of Norfolk, Virginia. Douglas F-3D Skyknights, Grumman F-9F Panthers, and McDonnell F-2H Banshees, the U.S. Navy's frontline fighters, were launched alongside British types. One test encapsulated the entire argument. A Douglas F-3D Skyknight was launched from Perseus with a 10-knot tailwind, meaning the wind was pushing against the aircraft, reducing its effective airspeed at the moment of separation. The existing American hydraulic catapult required a 30-knot headwind, the carrier steaming at full speed into the wind, to launch the same aircraft. The steam catapult had turned a 30-knot headwind requirement into a 10-knot tailwind capability. In operational terms, this meant a carrier with steam catapults could launch aircraft regardless of wind direction, in conditions that would ground a hydraulically equipped ship. 140 test launches were completed during the American visit. Perseus sailed for home on the 21st of March, 1952, and the prototype BX-S1 was subsequently removed and installed at the Royal Aircraft Establishment, Bedford, for ongoing shore-based testing and pilot training. The ship had done her job. The argument was over. In April 1952, the US Navy formally concluded that the steam catapult would be the most satisfactory type for service use. The word probably appeared in the original recommendation. Within months, it had been dropped. Manufacturing rights were obtained from Brown Brothers. This was not a gift, not a handover, and not an act of wartime generosity between desperate allies. This was a commercial licensing agreement between a Scottish engineering firm and the United States Navy, negotiated in peacetime. Norman Friedman, the American naval historian whose work on carrier design remains the standard reference, wrote plainly that the catapult was built under license in the United States as the C-11. British engineering drawings were redrawn to American standards, dimensions converted to imperial, materials specified to US Navy grades, tolerances adjusted for American manufacturing practices, but the fundamental design was Mitchell's. The first American steam catapult shot took place on the 3rd of December 1953 at the Naval Air Materials Center in Philadelphia. The Assistant Secretary of the Navy for Air, James Smith, pressed the button that launched a Grumman F-9 F-6 Cougar. USS Hancock became the first American carrier to receive steam catapults during her SCB-27 sea modernization at Puget Sound Naval Shipyard. On the 9th of February 1954, a 15-ton deadload was fired from Hancock's flight deck. Operation Test Fire, the U.S. Navy called it. The first manned launch from an American carrier followed on the 1st of June 1954, when a Grumman S-2F-1 tracker was shot off Hancock's deck near San Diego. From that moment, every new American aircraft carrier would be built with steam catapults. Every modernized older carrier would receive them. The hydraulic catapult was finished. The C-11 was the direct American production version of Mitchell's BS-4 design. It went into Essex-class carriers receiving the SCB-27C modernization, into the rebuilt Midway-class ships, and as waste catapults on USS Forrestal and USS Saratoga. The C-7, a larger variant, served as bow catapults on the early Forrestal-class carriers. Forrestal herself, commissioned on the 1st of October 1955, was the first aircraft carrier in history designed from the keel up with steam catapults, an angled flight deck, and an optical landing system. 3 British inventions integrated from the drawing board into the most powerful warship the world had ever seen. The angled deck was Dennis Campbell's idea. The mirror landing system was Nicholas Goodhart's. The steam catapult was Mitchell's. 3 British innovations made the American supercarrier possible, and none of the 3 inventors became household names in either country. We covered Randall and Boote's cavity magnetron and the Tizard mission of 1940, when Britain handed its most advanced military technology to America with practically no conditions attached. The steam catapult transfer happened 12 years later under different circumstances. It was a licensing deal, not a giveaway. Brown Brothers received payment, but the pattern was unmistakable. British engineers conceived the innovation, American industry built it at scale, and American power projected it across the world. The C-13 became the workhorse. First deployed on USS Kitty Hawk in the early 1960s, the C-13 retained Mitchell's fundamental slotted cylinder principle. The same twin pistons, the same sealing strip, the same water break retardation, but stretched and strengthened for aircraft that Mitchell in 1946 could not have imagined. The stroke length grew to 310 feet on the C-13 Mod 1. The cylinder bore increased, steam pressures rose as nuclear reactors replaced conventional boilers, providing virtually unlimited energy. In 1982, a Naval engineer named Modest Zakharchenko developed the C-13 Mod 2, nicknamed the Fat Cat, a 21-inch bore low-pressure variant that reduced the punishing maintenance demands on Nimitz-class carriers and saved the Navy over $600 million across the fleet. Every one of the 10 Nimitz-class carriers in service today carries 4 C-13 variants, 40 steam catapults on 10 ships, all tracing their lineage to a factory on Broughton Road in Edinburgh. Mitchell did not go unrecognized by the people who understood what he had done. In 1946, he received the OBE for his wartime service. In 1955, the Franklin Institute in Philadelphia awarded him the Newcomen Gold Medal. And he was the first person outside the United States ever to receive it. In 1958, President Eisenhower conferred the United States Medal of Freedom, accompanied by a plaque inscribed with 8 words, "No one man has contributed more to the carrier navy." In 1962, he was elected Fellow of the Royal Society of Edinburgh. He served as Scottish branch chairman of the Institution of Mechanical Engineers. After his death on the 21st of January 1969, at 64, the Royal Academy of Engineering established the Colin Campbell Mitchell Award, an annual cash prize for engineers making outstanding contributions to British engineering, commemorating what the Academy called one of Scotland's most accomplished marine engineers. The award is still given. So here is the question that the facts force you to ask. A man receives the OBE, a Medal of Freedom from an American president, and the first International Newcomen Gold Medal. A man has an engineering prize named after him that is awarded every year. How can this man be forgotten? The answer is that there are two kinds of recognition, and they operate in entirely different worlds. Institutional recognition, medals, fellowships, professional awards, exists within a closed system. Engineers know about the Newcomen Medal. Fellows of the Royal Society of Edinburgh know who their fellows are. The Institution of Mechanical Engineers published a detailed obituary. Within these circles, Mitchell was honoured, respected, and remembered. But institutional recognition does not cross the barrier into public awareness. There is no biography of Colin Campbell Mitchell. There is no documentary. There is no chapter in a popular history of the aircraft carrier that puts his name in the title. When television programs show the spectacular image of a jet launching from a carrier deck, no caption appears explaining who made it possible. The image became one of the most recognized symbols of military power in the 20th century, and it became completely detached from the man who created the mechanism behind it. The institutions remembered, the public never knew. Mitchell died 8 months before Neil Armstrong walked on the moon. He did not live to see the Nimitz class carriers that would carry his catapults for the next 6 decades, or the French nuclear carrier that would buy American-built copies of his design, or the moment in 2017 when the USS Gerald R. Ford finally broke the steam monopoly with an electromagnetic system, 63 years after Hancock's first launch. He did not live to see the argument over whether his invention should be replaced at all. That argument is worth pausing on because it tells you something about how good Mitchell's engineering was. The electromagnetic aircraft launch system, EMALS, was developed by General Atomics to replace steam catapults on the Ford-class carriers. The concept is elegant. Instead of steam driving pistons through cylinders, an electromagnetic linear induction motor accelerates the shuttle along the deck track. No steam, no pistons, no sealing strips, no water brake retardation cylinders, no 2,000-degree steam venting across the flight deck between launches. EMALS offers smoother acceleration, finer control over launch energy, lower peak stresses on airframes, and dramatically reduced maintenance. On paper, it is superior in every measurable way. Gerald R. Ford was commissioned on the 22nd of July 2017. The first manned EMALS launch, an F/A-18F Super Hornet, took place 6 days later. By 2025, Ford had completed over 22,900 successful launches and recoveries. The system works. The next 3 carriers in the class, John F. Kennedy, Enterprise, and Doris Miller, are all being built with EMALS. The steam catapult's replacement is no longer theoretical, and yet the 10 Nimitz-class carriers cannot be retrofitted with EMALS. Their nuclear reactors generate enough steam for catapults, but not enough electricity for electromagnetic launches. Replacing the power generation system would mean rebuilding the ship. So the Nimitz class will continue operating with steam catapults until the last hull is decommissioned. USS George Washington, the oldest, is scheduled to serve until the late 2030s. USS George H.W. Bush, the youngest, will not retire until approximately 2059. 33 years from now, American pilots will still be launched from carrier decks by Mitchell's slotted cylinder principle, a concept he first patented in 1936, 123 years before it finally leaves service. The French Navy tells a similar story from a different angle. Charles de Gaulle, France's only aircraft carrier, operates with two C-13-3 steam catapults, shorter variants of the Nimitz class units, 75 meters against 95, purchased from the United States. American built, but Mitchell's design at their core. France's next carrier, officially named France Libre by President Macron in March 2026, will use 3 EMALS tracks purchased from General Atomics at an approved cost of $1.32 billion. Even the price tag marks the transition from a technology that a Scottish firm licensed to America for undisclosed but presumably modest terms, to a replacement system that costs more than the GDP of some countries to acquire. China chose a different path entirely. The People's Liberation Army Navy skipped steam catapults altogether. Their first 2 carriers, Liaoning and Shandong, use ski jump ramps, which limit aircraft to lighter takeoff weights and reduce combat radius. Their third carrier, Fujian, completed in 2022, went straight to electromagnetic catapults of Chinese design. In September 2025, video confirmed successful launches of J-15T fighters, J-35 stealth fighters, and KJ-600 airborne early warning aircraft. China looked at Mitchell's 60-year-old technology and decided to leapfrog it rather than license it. Whether their electromagnetic system matches EMALS in reliability remains to be seen. The Americans spent over a decade working the problems out, but the strategic calculation was clear. Steam was the past. Electromagnetic was the future. There was no reason to pass through the intermediate step. So the era is ending. Not suddenly, not dramatically, but with the slow inevitability of ships aging out of service and being replaced by newer ones. The last steam catapult launch from an American carrier will happen sometime around 2059, and no one will mark the occasion because no one outside the engineering community marked the first one either. What remains is the ledger. Between 1954 and 2026, 72 years, American steam catapults have launched hundreds of thousands of aircraft. Every combat sortie flown from a US carrier deck. In the Vietnam War, the Gulf War, the wars in Iraq and Afghanistan, the strikes against Libya, the patrols over the South China Sea, every single one began with Mitchell's mechanism. The A-6 intruders that bombed Hanoi, the F-14 Tomcats that patrolled the Mediterranean, the FA-18 Hornets that struck Baghdad, the EA-6B Prowlers that jammed enemy radar, the E-2 Hawkeyes that controlled the airspace, the S-3 Vikings that hunted submarines, the C-2 Greyhounds that carried mail and spare parts. All of them sat on a shuttle, connected to twin pistons, inside slotted cylinders, and were hurled off the bow by steam. Mitchell's catapult did not merely launch aircraft. It made a particular form of global power possible. The nuclear-armed supercarrier, a mobile airfield carrying 70 aircraft, operating anywhere on the world's oceans for months at a time, capable of projecting decisive force over distances that land-based air power cannot reach, could not have existed without a reliable, scalable, maintainable catapult. The angled deck allowed simultaneous launches and recoveries. The mirror landing system allowed safe approaches in poor visibility. The steam catapult provided the raw energy to put heavy aircraft into the sky. Remove any one of the three, and the supercarrier as an instrument of power collapses. Mitchell's contribution was not decorative. It was structural. The Imperial War Museum holds photographs officially labeled the Mitchell Steam Catapult, An archive of his personal papers was sold at Bonham's. The Institution of Mechanical Engineers published an obituary that noted the steam catapult led to very large export orders for Brown Brothers, suggesting the company did well from the American license, even if the exact figures were never made public. The Royal Academy of Engineering gives out a prize in his name every year to young British engineers. These are real things. They exist. They matter to the people who know about them. But here is what does not exist. There is no museum exhibit that tells the story of how a Scottish engineer in an Edinburgh factory solved a problem that the United States Navy, with all its resources, could not. There is no plaque on the building at Broughton Road. There is no chapter in any popular history of naval aviation that centers Mitchell's name. When documentaries show that spectacular footage, the steam, the 2-second acceleration, the jet leaping off the deck, they do not pause to explain who made it possible. The image crossed into the public imagination, completely severed from its creator. American power, British invention, and between the two, a gap wide enough for one man to disappear into entirely. Colin Campbell Mitchell designed an arresting gear system in his 20s, patented the core principle of the steam catapult. At 32, discovered the Germans had proved him right. At 41, built a working prototype by 46, convinced the most powerful navy in history to adopt it by 48, and died at 64 in the city where he was born. His catapult launched aircraft for 20 years before his death and will continue launching them for 33 years after this recording. Presidents signed medals for him. Engineers named a prize after him. The public never learned his name.